Hey guys, welcome back to my channel and let us look at a recursive algorithm of finding chromatic polynomial for a graph. Okay, this is part 3. You can check out the part 1 and part 2 in the playlist I tab above. Okay, let us begin. So suppose we have lambda colors. Okay, for any, let us take any graph. For example, let us take a graph on 4 vertices. Okay, we will find a recursive definition where for any graph you can iteratively find the chromatic polynomial for that given graph. Okay, so we will take, suppose this graph, let us label the vertices a, b, c, d. Okay, now we have to find the chromatic polynomial for this graph. Okay, so how do we do that? Okay, so let us before the recursive algorithm, let us check without the recursive algorithm how would we proceed. To any of the vertices, let us say, to how many ways can you color this b vertex using lambda colors. You have b choices, we have lambda choices, any color you can use over here. Now you have colored this vertex, we will move to this neighbor c. Now as c, only one vertex has been assigned color. Now one color has been assigned to b out of any lambda. So C cannot have just this one color. So it has lambda minus 1 remaining choices. Now suppose let us move to D. Okay, D is adjacent to C and D is adjacent to C and C has been assigned one color. A has not been assigned any colors as of now. C has been assigned one color. So D cannot take only that color. So it has remaining lambda minus 1 choices it can choose from, except this C, whatever color C has been given, this cannot be taken by D. Now what about A? Now note, A is at B has been assigned a color, C has been assigned a color, D has been assigned a color. So, but B and D, they are not adjacent. So, there can be two possible cases. B and D can be of same color, or B and D can be of different color. So, I can break this problem as, suppose B and D, they have different colors, right? That means different colors mean I can convert this problem as B and D as having assigned different colors. That means we can join B and D. Then also they will be assigned different colors because we are seeing proper colorings. Adjacent vertices cannot have the same color. Okay, so this A case becomes same as this graph, number of ways you can color this, and then plus, okay, B and D can be of same color, right? That means we can merge B and D into a single vertex. So I can create A is adjacent to B, right? So B and D has become the same vertex now, okay? And then B is adjacent to C. Okay, we'll make C over here. A is adjacent to B, B is adjacent to C, C is adjacent to A, C is adjacent to A, then C is adjacent to D, like this, and D is adjacent to A. D is adjacent to A, like this. So this problem is reduced to how many ways you can color this first case graph and second case graph. Okay, I have hope you have understood how I broke this problem into two different problems. Okay, so what we can do, this complete graph on 4 vertices, I can move on the LHS side. So what we will get is, let us write the number chromatic polynomial as a function C, which takes input a graph. Let us make this graph the complete graph on 4 vertices. Okay, like this. Okay, let us make it properly. Okay. So when we have lambda colors, okay, this will be equal to, we have brought this on LHS side, right? So what we have the number of ways you can color this graph. That means we have removed the edge. This is A, B, C, D. We have removed the edge BD, right? So we will call this edge BD as E. We have removed this edge E. Okay. Okay. AC edge is there. So you have removed this edge E or BD from the complete graph minus, because we are bringing this part over LHS side, so it become minus, merging the vertex BD together, right? The vertices BD that were incident on the edge E, they are now merged or combined into a single vertex. Okay. Oh, okay. Yeah. A, B, D, C. So chromatic polynomial for this graph using lambda colors. So this is the definition of the recursive algorithm. Iteratively, what you can do if you have any graph, no matter what graph you have, if you can find the chromatic, you can break this, the number of ways you can, the chromatic polynomial for this complete graph or any graph, any graph you choose, you can remove any edge from the graph, that minus the you have to merge the end vertices of that edge into a single vertex. So this is the recursive definition of finding the chromatic polynomial for any graph. Okay, this is called the, see it is over here, this is called the deletion contraction principle, where you delete any of the edges from the original graph. You delete any of the edges. The edge has been, E has been deleted. So I can rewrite it as, in the textbooks you will find it like this. If this graph is G, chromatic polynomial for the graph G using lambda colors will be equal to the chromatic polynomial of the graph G minus this edge E. You remove this edge, delete this edge, minus, okay, be careful, this is a minus over here. I explained you why this is a minus over here. Chromatic polynomial, when you contract these two incident vertices as a single vertex, contract the edge E. Okay, G dot E means contraction of edge E into a single vertex comma lambda. So you can use this to code and find the chromatic polynomial of your graph recursively. Okay. Uh, Hope you like this video. Please share it with your friends. Subscribe to my channel and stay tuned for more discrete maths videos. Bye bye and take care.